Welcome everyone to the fourth, I believe, Flow talk. So Flow, as you know, is the Federated Learning One World seminar. We have a website, we have a YouTube channel, we have a Twitter account as well. And what we want to do, we want to offer the top researchers in the field of federated learning, very broadly interpreted, to give them the chance to give talks on the recent, or maybe not so recent, but fundamental research across all the areas which touch on federated learning, which is algorithms, cryptography, optimization, privacy, compression of communication, systems, hardware, and so on and so forth. So this is what this is about. And let me briefly introduce today's speaker. So this is a great pleasure to have Praneeth Karimireddy give the talk. Praneeth, he is interested in several areas, including machine learning, theory, algorithms, large-scale optimization, collaborative learning, high-dimensional statistics. He has a bachelor degree from IIT in New Delhi, and since about 4 years ago, he's been a PhD student at EPFL, working under the supervision of Martin Yagi. So again, it's a great pleasure to have you, and feel free to start whenever you're ready.
Thanks, Peter. So today, this is joint work with Satyan Kale, Mehriyar Mori, Shashank Reddy, Sebastian Stee, and Anandatirtha Suresh. So this was partly done when I was interning with Google last summer. It's a new algorithm called SCAFFOLD for federated learning. Okay. So just so that first for questions, I have the chat open on the side. So if anyone has questions at any point, feel free to type in the chat and I'll take a look. But otherwise, I'll pause for questions regularly and feel free to ask over audio then. Okay. So there are like three main contributions, three main parts to the talk. So first is we have a new tight analysis for federated averaging when we have heterogeneous clients or this non-IID data. So these are like the main takeaways of the talk. Then we show that there is a degradation in the performance of this federated averaging, and this is because of something called drift in the client updates. And then finally, we'll see this new algorithm. It is very resilient even if you sample the clients. So I just want to talk briefly about the setting because I think each of us means slightly different things by federated learning. So just so that we're all on the same page. The setting I'm looking at is there's a server, say this is some cloud provider who has a server model. This could be, for example, Google. And then there's a lot of devices which have the local data, and these devices which have the local data, we call them clients. These could be hospitals, these could be mobile phones, whatever. So the algorithm proceeds in rounds. So the setting was introduced by Brendan McMahon and others in 2016. And the algorithm, we look at all the algorithms we look at proceed in rounds. In each round, a subset of these clients are chosen. Say we represent them by this script S. And then the server sends a copy of its model to these clients. The clients make a copy, so we call, suppose the server parameters is X, the client parameters, we call them Y. Then the client does some updates using its own local data. These updated models are then sent back to the server. The server performs some aggregation and this becomes the new server model. And so this is like the high level overview of what algorithms in federated learning setting look like. And this round repeats again and again. So there are some characteristics of federated learning which make it distinct from the usual distributed learning setting. So there is a high overhead per round to communication. So this means that we really want to reduce the number of rounds of communication to as little as possible. In uh, the amount of time it takes for the client to make its local updates, we don't care so much about. Then the second thing is in each round, only a few clients probably participate. We cannot expect all the mobile phones or all the hospitals in our network to be online all the time. And so there is necessarily sampling happening. And the third characteristic is that the data amongst the different clients is heterogeneous. That means the data on one hospital is quite different from the data on in a different hospital, or the data on my Android phone is quite different from the data on your phone, and so on. And fourthly, in this talk, we restrict ourselves to when the total number of clients are either small or medium, like say a few thousands. So this is called the cross silo setting. Basically what this means is the number of clients cannot be in millions or whatever. We need to see each a client at least a few times. It's not that it appears once and then we never see it again. So how do we formalize this? We say, okay, we have, we want to minimize some objective. We want to minimize some loss function. Here, X refers always to the model parameters. This Fi refers to this loss function with respect to the parameters and the client I. We take an expectation over the local client data. And then we take a weighted average of this loss function across all the clients. Okay, so this is the objective which we'll be working with. Maybe at this point, if there's a question. Yeah, okay. So the question is about the data distribution. No, so the data distribution is different across, we make no assumptions so far about the data distribution. It can be arbitrarily different for different clients. Yeah, the zeta should probably have a subscript I. Okay, is there any other questions regarding the setting? Okay, so let's briefly look at some algorithms for this setting. The simplest algorithm is just SGD. So what would SGD do? In each round, say we sample this subscript S clients, right? So for each of the sample clients, we just compute a large batch of, we just compute a stochastic gradient, which is this GI, of X. So this is the gradient computed at X on client I. And then we just average this across, okay, yeah. So we take a batch size of K. Each client computes a mini batch gradient of size K. And then we average this across all the clients and we use that to update our model parameters. So this is just doing mini batch gradient. So it's an algorithm which we're all familiar with. So this is good because it's an algorithm we all know. It's equivalent to what we would do in the centralized setting. And so it converges for sure, but it is very slow. So we're just taking like one update. So the clients are not really doing much work. They're just computing the one gradient and sending it to the server. And so because we are only doing one update, it's potentially very slow. And then probably the most popular algorithm in the setting is this algorithm called federated averaging, which is also in some other settings known as parallel SGD or as local SGD. They're all very similar algorithms, or if not identical. So in this federated averaging, each of the clients which have been sampled, instead of just performing one step, we say, okay, we want to do more work before we communicate because communication is expensive. So we do K updates locally. So we do K such updates, and then we communicate to the server. And the server takes this new updated parameters and just averages it to compute the new server parameters. So this is nice. So now instead of just doing one update per round, we're doing K updates per round. So it's potentially faster, at least we would hope so. But now because we're doing K steps per round, this algorithm is now quite different from just doing the centralized updates. And as we will see, this difference may lead to some divergence issues and instabilities issues. Yeah, so there's a question about whether these updates happen in parallel. Yes, so both in the SGD setting as well as in the federated average setting, the updates on the client I happen in parallel. So there are K updates happening within each client. This happens sequentially, but across the clients I, they're happening in parallel. Yeah, this is important. Okay, so our new algorithm is SCAFFOLD. What we stick to basically the same structure as Fed averaging, but we just have a new correction term. So we will see that we just have the same overall structure as Fed averaging. We'll perform K updates, but we'll add the correction term which will apply to each of our updates. So like federated averaging, this is faster because it potentially faster at least because it performs K updates per step per round before communicating. And we'll see that by adding this correction, we can actually make SCAFFOLD mimic the centralized updates much closer. And it has much better convergence properties. So this was like a brief summary of the talk so far. So maybe I think this is a good time to pause for questions if anyone has questions about the setting or about what we're going to see.
So feel free to continue mentioning some comments here in the comment section, but you can also raise your hand, in which case your Samuel will try to unmute you and then you can ask your question yourself.
Yes, so there's a question about how this correction term looks like. We'll get to that, but just to say, this C is the same for, so whenever you see a subscript I, that means that this is for the device I. So here, this is CI is specific to client I. If there is no subscript, it means it's a global quantity. So this is the same across all devices. But we'll see what this algorithm actually looks like later.
Yeah, but of course, all of these things iterate. You're just keeping the iterate
yes,
indices.
This update repeats K times within each round, and each round repeats again and again. Yes, so there's a question about the SGD update. The SGD update computes all the gradients at X, so at the server parameters. This is exactly what we would do if we were computing a mini batch SGD step. Everyone computes for SCAFFOLD. Yeah, so for SGD step, all the gradients are computed at X. In federated averaging, the gradients are computed at yi, which is the local client parameters, and it's the same in SCAFFOLD. Oh, oops, sorry, this was a typo. This should not be X. That should be that should be yi. That's a good catch. Thanks. Yeah, I repeat, this should not be X, this should be YI. Okay, so there's a question about the size of S. So size of S, think of it as being something like 10% of the total number, or at least in this talk, you can think of it as being something between like 1 and 10% of the total number of clients. So if there are 1,000 clients, 100 participate in each round.
Does your theory depend on that assumption, or this is just a practicality?
This ratio does affect the rates. Yeah, we'll come. It comes up even in the theory.
Yes, but the question is, can you in theory handle any number, any cardinality of S from one to everything?
Yes, yes. It's just the rates may not be meaningful in some of these settings.
Okay.
Okay.
I don't see more questions.
Nice. Okay. So so now I want to sort of pause and examine this federated averaging for a bit and see what might be the problem. So there have been actually a series of papers recently which all show experimentally that if you have this heterogeneous clients, which means that the data on each of the clients is different, federated averaging actually has a pretty significant drop in performance. For example, if you take some CFAR thing and you run this federated averaging algorithm, you don't really do better than just random guessing. So it's not doing anything. So I want to try and understand why is this happening. So to see this, let's take like a simplistic setting. So here in blue is the loss function F for client 1. So in the setting, we're just looking at just 2 clients. Suppose there are just 2 clients. Client 1 has the loss function F1 and client 2 has a loss function F2. And I've drawn some, I think these are called contour plots of the loss function.
So there's a question here by Konstantin.
Yes.
I believe I unmuted you.
Yeah. Hi, Praneeth. The question is about the experiment with heterogeneous data where locus GD doesn't work well. Can you just give a bit more details how exactly heterogeneity is obtained here?
Here, I think it's okay. It's actually not. So I would recommend reading this paper for more details. It's not so straightforward. I don't want to screw up the description, but okay. We'll also see some heterogeneous experiments in this talk, and I can give more details about that part. Okay. Yeah. So 2 clients, loss function of client 1, loss function of client 2 in red, and in green in the is the average of these 2 loss functions. So this in green is a true global loss function. These functions are not really, ones which I've drawn are not really convex. So we'll deal with both convex and non-convex things in the talk. At least in this picture, I doubt these are convex functions. But that doesn't matter for the intuition. Okay, so let's see. Oh yeah, so our goal is to get to this green triangle, which is the global optimum. Okay, so suppose we start at this green dot xt, and so what does SGD do? SGD computes update on F1, computes a gradient on F2, and it averages it and goes here in the green part. Again, in the next round, compute a gradient on F1, compute a gradient of 2, take an update step. And so as you keep moving, this trajectory converges to the true optimum. And in particular, if you start at the optimum itself, you have your gradient of F1 in that direction, gradient of F2 in this direction. And when you average them out, they exactly cancel and you remain at the optimum. So the limit point of SGD is the true optimum. Everything is nice. Now, what happens if you do the same thing with federated averaging? So in washed out green is the SGD updates for comparison from previous step. Now we'll see, so in the first, if you just take one step, one local step on F1 and one step on F2 and average them, you get back the same SGD update. But now let's see what happens if you do more than one step. So now you have two steps and this is the new average step. Now you take one more step and now this is your new average step. So if you take 3 updates on F2 and 3 updates on F1, you sort of moved away from the true path towards the global optimum. And you're moving sort of closer towards, you're moving away from this point and closer to some other point. What is happening here? Essentially what is happening is if you run this local updates long enough, this point, so yeah, if you run the local updates long enough, you will converge to the optimum of F1. And if you run the local updates of F2 long enough, you'll converge to the optimum of F2. And now when you average these two things, you actually converge to the optimum of, you converge to the average of the optimum of F1 and F2 and not to the true global optimum. So in particular, suppose we just start at the true optimum. F1 will go somewhere there. Updates of F2 will go somewhere there. And when we average this, you will read somewhere here. And this difference, so this means that even if you start at the optimum, you move away from the optimum. So this is what we term as drift in this paper. So essentially, federated averaging is not really optimizing the function you want it to optimize. It's doing something else. The point it converges to is some weird combination of the average of the optimums and the true global optimum. I think actually Peter and Philip have a paper which details about what is federated averaging actually optimizing. But okay, so this explains why federated averaging is not really working in our case. It is not really optimizing the function we want it to optimize. And so if we want this point in the circle to be close to the triangle point, the only way to do this is to use a very small learning rate so that this difference gets smaller and smaller. And this is not, yeah. So it's just showing that, okay, there's a gap. Oops. So this is, this actually shows up in the theory too. So if you look at the rates for SGD, for strongly convex, it's something like this. So here sigma is the variance within a client. R is the total number of rounds we perform. K is the number of steps we take per round. And N is the total number of clients. So for now, let's assume all clients are participating just for simplicity. So the rates for SGD in the strongly convex case look something like this. And similarly, you have some rate in the non-convex case. So importantly, notice that there is like a term here, which depends on sigma, which we call the statistical term. And there's the second term, which is doesn't depend on sigma, and this is the optimization term. So this is true for both in the convex and the non-convex. This is the statistical term, and this is the optimization term. It turns out that all of these algorithms, as long as you compute equal number of gradients, it doesn't really matter where these gradients are computed. Noise is just noise, and SGD don't care, as this nice paper says. And so all these algorithms will get the same statistical term. So we don't care about the statistical term, and we just replace this by like a script, and our focus is on what happens in the other terms. Okay, so SGD has these rates. And if you compare it to, so yeah, federated averaging, so if you believe my previous picture, it should, it really, it should slow down. It should be worse than SGD. And in fact, we need some additional assumptions to even prove that federated averaging converges. So we need to make some assumptions that the gradients across the clients satisfy some sort of similarity. Like this is essentially saying that the variance of the gradients across the clients is bounded by G square intuitively. This generalizes a few notions. This I think a very similar notion was presented by Khaled Ahmed in 2 talks ago. Yeah, and with this new assumption, we can prove some rates. So we can show that okay, so we have the same noise term as before, we have the same optimization term as before, but now we have this new term. So this new term is a result of this drift we saw, that this federated averaging is not really optimizing the function we want. To make it optimize the function we want, we need to choose like really small step sizes, and this makes it much slower. So similarly, so okay, so these were these, so on left is the rates for SGD, right is the rate for federated averaging. So just like in the strongly convex case, we can also prove some rates in the non-convex case. So in the non-convex case, we saw that SGD had this rate. So for federated averaging, the optimization term remains the same, but now there's a new drift term which appears, which slows down the convergence. So these rates are the tightest rates for federated averaging as far as we are aware. And
so there's
and
a question here. I'll interrupt if you don't mind, and Tin Gon is going to ask himself.
So is this a new HR term in federated averaging is worse than the noise term?
Sorry, could you repeat the question?
The term, the term in the middle of federated averaging, is this worse than the noise term?
That's a good question. So these are independent quantities. It really depends on the setting. In some setting, this term might be bigger. In some settings, this term might be bigger. Though typically, if you're looking for low levels of accuracy, or if the so suppose you take suppose the variance within the clients is not that much, then the first term is quite small. So if you remember, the script N depended on the variance within each client, whereas G controls the variance across the clients. So it depends which you think is bigger. Typically, this term is actually bigger. At least experimentally, if the experiments are to be believed, this term is quite significant.
Okay, thanks.
There's a question about why B is not in the convergence rate. All these rates are simplified. They're like some constants missing. I would refer to the paper to see the dependence on B. Yes, so yeah, there's a question. There's actually a trick we had to do, which so there's
Praneeth,
a reason why.
Can I ask you to read the question before you answer? That'd be quite helpful. I could do that as well if you prefer that.
About the step sizes?
No, in general. So, if
yes,
you could read the question before you answer,
yes.
that would put it in context.
Yes.
But I'm happy to do that as well if you want me to.
No, that's a good point. Yeah, there's a question. There was a question about why B is not in the convergence rates. It's not in the convergence rates because I didn't write it in the slides for simplicity. It's in the paper has the exact rates. And there's a second question about what is the step size which was used to get these rates. This is an excellent question. because there's a reason why our rates are tighter than any other rates. We actually needed to use 2 step sizes. We have a client step size, and we also have a server step size. Essentially, what this means is this has been explored in other papers too. So I would just refer to the paper for this, and yeah, for the exact step size, which and so on, I would just refer to the paper. It's some messy expression. Yes. Okay. So now we have some upper bounds, right? We have some upper bounds which shows that the rates for federated averaging is actually slower than SGD. Oh, sorry. There's a question about is using this 2 step sizes actually helpful in practice? We don't do this experiment, but there's this paper by Shashank Reddy and Zach, which is called Adaptive Federated Optimization. They do extensive experiment. It's like a more empirical paper, and they show that using this 2 step sizes is actually quite important if you want to get performance. Yeah. So practically, so yeah, apparently in practice, this is a super useful thing to use these 2 different step sizes. Yes. Yeah. So we said that the rate for federated averaging is slower because there's this additional drift term, but these are just upper bounds. Is that really necessary? And it turns out it is. We cannot really get rid of this this term. So we show like a simple example. These are just like 2 functions which are scalar quadratic functions, and we show that federated, as long as you take greater than 1 local step, so if k is strictly greater than 1, you can tune your step sizes adaptively, or you can pick them in advance. Sorry, you can pick them arbitrarily. You cannot beat this. You cannot get rid of this. So there is a small gap between the upper bound and the lower bound, like there's like a kappa factor, condition number factor. It's not clear whether, I don't really know which of these 2 is tighter. Maybe you can get rid of this and get a better lower bound. But at least this shows that you will necessarily be slower than SGD. And this is not just a theoretical result. Nathan Srebro commented that they have a tighter lower bound, which actually shows that this mu square is necessary. So so yeah. So this means that basically you cannot improve upon this. It's nice. So there's a question from Nate Pham, which says, the question is 1 step always larger than the other? I'm not sure which of the 2 you're referring to. Okay, between federated averaging and SGD. Yes, the step size for federated averaging is always smaller than the step size for SGD. And we'll see like a quick experiment where this is true. So this is just like a linear. So all the people who zoned out because we were talking about weird symbols, you can take a look. So this is a simple experiment with just as linear regression on some data set from UCI. We partition this data set onto 10 clients. This partitioning is done by because the regression data set, we can just sort the Y values and partition accordingly to the sorted values. So we run SGD on this. Oh yeah, and everyone takes 10 local steps. Sorry, federated averaging takes 10 local steps. SGD, of course, just takes 1. So SGD is this in purple. SGD's step size was tuned, and we get some nice convergence like this. Lower is better. And then we see what is the step size for federated averaging which works. So in blue, if we take the divide the step size by 10, it's still slower. And then we divide it by 50. Now this is better. And then this is by 200 and by 500. So this shows that actually doing the step size by, you need like a 50 times smaller step size for federated averaging than for just SGD. So federated averaging necessarily needs a smaller learning rate, and this makes it necessarily slower than SGD. This is not just a theoretical result. You actually see this in practice. So yeah, so this hopefully, so in summary for this section, there's this thing called client drift, which happens if you take more than one local step. And this client drift makes it necessary for federated averaging to use a very small learning rate. And because federated averaging needs a very small learning rate, it is often slower than just doing SGD. I can pause for questions if there are any for this section. There's a question which asks, is this problem purely stems from heterogeneous data, right? Yes, this is this problem is so as we illustrated here, this problem is happening because when you do federated averaging, you don't really go to the true optimum. So this is only a problem if the optimum of F1 and F2 are far away from each other. If the optimum of F1 and F2 are the same point, then federated averaging is pretty good. There's a question which asks, how does sampling affect this? Sampling, it basically changes what this noise term is. It introduces some, so if we look at the rates for federated averaging, so here this noise term changes. The rest of these two terms remain the same. Yeah, sampling doesn't change the picture overall too much. So you can refer to the paper for exact rates, what happens with sampling. Okay, so then I think I'll move on. So okay, federated averaging has this problem, but we still want to do local steps. So what do we do? The main idea is to add this. So this is this correction term, which I talked about like at the start very briefly. We just add a correction term to make sure you're optimizing the correct objective. So you make a guess for the server update direction. So you have a guess in which the server is going to move. Let that guess be the solid green line. In general, the server is moving in this direction. That's what this arrow is telling us. And then you also have a guess for how each of the client is moving. So in general, client 1 wants to move in this direction and client 2 wants to move in that direction. And then you say, okay, so in general, my client wants to move here, but I actually want to move here. So I will I will take this difference between these two and use this as my correction step. So these are the correction terms from the previous slide, the ones with the hollow arrow. So these are the correction terms from before. Again, this should be GI of yi, not GI of x. So this is the gradient which is computed at the current client parameters. So this is a typo. Okay, so this is the gradient we compute. And then instead of going there, we add this correction step, and then we go here instead. Again, compute the gradient. Again, don't go there, add this correction, come here instead, and repeat. So similarly for the other client, you go there, compute the gradient, add this correction, compute the gradient, add this correction. And now you can see that, okay, at least intuitively, this keeps the updates of the scaffold algorithm much closer to the usual centralized updates. If our guesses are good, then we follow these centralized updates much more closely, and intuitively this fixes this issue of client drift, which we talked about before. But how do we actually get these guesses? Okay, so you basically sort of start with an arbitrary guess, say all zeros. And then you just see in my previous round, how did my gradients on client 1 look, and take an average of these two. So initially I have some guess, I compute all these updates, and then I see how my gradients look. I average these gradients to compute my guess for CI for the next round. And the same for the other one. We see, okay, this C2 uses this as the gradients, just average these and use this as the guess for the next round. And the global C is just the average of these two Cs. So this is the scaffold algorithm. It is exactly the same as federated averaging, except we add this. Yeah, so here it's fixed. The gradient is computed at yi. So it's exactly the same as federated averaging, except that there is this correction term. And this correction term has to be updated. So at the end of each round, we compute these guesses, which are called control variates, by either averaging all the gradients we have seen in the past round, or computing like a new batch of gradients at X. So this describe and a quick demo. So we saw previously that the best step size for federated averaging was actually, you needed to reduce the step size by 50 times to make it converge.
There's another question here. Apologies for interrupting.
Yes.
By 10.
So could you interpret more how the variable C is updated? So it's updated every iteration, or after the communication to the server?
It's updated every round. So which means after every time you communicate to the server.
Okay, so if you implement case a step of the local gradient, then every case C will be updated, right?
So in the local steps, this C is fixed.
That's right. Yeah, that's what I mean. Yeah, thanks.
Yes. Nice.
So I would ask one question. So in case you do just one local step, can you set all these C's to just zeros?
Yes. So if we do just one, if K equals 1, the C's don't really, so we always make sure that this C, the server C, is the average of the client C's. So if we don't do sampling, so if all clients participate and we do only one step, this just becomes equal to SGD, and you can just get rid of this C's. We'll come to what happens with sampling a little later.
Yes, and your theory, your general theory recovers that, right? You could set them to 0, and that's the optimal choice somehow.
Oh, you mean at
updates.
Initialization, or?
Well, say the initialization is 0. So how would your theory then predict that these C's should stay at 0? So does it mean that you set the step sizes to be infinite, or
so if you have
for the update
K
of the
equals,
C's?
So if you have K equals 1 and there is no sampling, then these C's just cancel out, because the average of CI is equal to C. When we average the updates of the clients, these just cancel out. And so it doesn't matter what C is.
Sure,
Can
but
we
when
set
you
arbitrary?
update them, is it clear that the update will be nil?
They might not remain 0, but it doesn't matter.
Okay, okay, I see. Okay, that's what I wanted to know. Thank you.
Yes. Yes. Any other questions about the description of the algorithm?
Yeah, I would also have a question.
Yes.
About your construction of CI. So you said
Right.
you just set it as the average over this k steps over the gradient that you're gonna see over this k steps. Isn't
Yes.
better idea just to set it as the last gradient you saw? Because that potentially that could be like a better estimator of the current geometry.
That's a good point. Yeah, so it's theoretically, at least, it's actually quite robust to how you set the CI. Pretty much anything reasonable you do, the theory works. I'm pretty, so we didn't really try this, but I think there's someone in the lab who tried this, and they reported that, in fact, experimentally, if you set the CI to be the gradient computed at the end, it performs better slightly experimentally, but theoretically it's all the same. Anything reasonable works.
Thank you.
That's a great question though.
There's a question by David Frey.
Yes.
I believe I unmuted you. Okay, not sure whether this was intentional or not. So I guess maybe just read and respond to these questions that I can see in the chat. And
Yes.
if David,
Is there a link?
yeah.
So there's a question. Oh no, David asks, can you hear us? We cannot, unfortunately.
No, we cannot hear you.
Afshin asks, is there a link between scaffold and variance reduction? Yes, I was just about to come to that. That's a great observation. So yeah, so this just shows that if you pick the same learning rate so this learning rate was tuned for SGD, you pick the same learning rate, scaffold converges, and it converges faster than SGD. And it's much better than this federated averaging. So that's it. It's not just theory, it also works in practice.
I think there was one question even before this question by Naifu. I don't know whether you answered that one at least.
No, yes, thanks.
Yeah.
There's a question about CI and C depend on X, so you assume that C changes slowly. Yes, so why can we do this? What is the intuition for why this makes sense? The reason why we can use the past gradients as a guess for how the update is going to look in the future is because we assume that the functions are smooth. So if the functions are smooth and you don't move too much, then your past gradients will sort of look like your new gradients, and that's why this makes sense. That's a good and this also ties to the variance reduction question which Afshin asked, which I'll come to next. So there's a question from David Frey, which is, I was not sure how you compute the CI. Is it the aggregation of the previous gradients for J not equal to I? No, it is just the previous gradients for I. So CI is the gradients for I. C minus CI is intuitive, is actually what you mean. So C minus CI is the gradients of all the other clients which are not equal to I. Hope that answers this.
So I would have one more question. So as you said, because this is like linked to variance reduction. So also you would kind of suffer this problem that for scaffold you need to assume that you have the smoothness over like the whole function, and rather than like for SGD, you need like the smoothness with just respect to the optimum, or as in some paper they refer to it like expected smoothness, right? That would be something that like that might be the regime in which like scaffold will perform like worse, because this like this L constant one, like that L constant that appears in like classic SGD, that can be potentially much smaller than what you would need to have for scaffold.
Yes, that's true. We need to assume that each of these functions fi is smooth, not just the global function f. That's true. And yeah. So like Ashin observed previously, this is actually very closely related to this variance reduction. In fact, if you do sampling and if you do only one local step per update and you sample your functions, the algorithm you get is actually equal to Saga. So Saga is a special case of scaffold. Another way to look at this is because if this correction is very good, then just one client on its own gets pretty good performance. Like we don't even need the other client to try mimic the centralized update. Every client's updates are close to the centralized updates, and this is essentially why we can get these variance reduced rates. So if anyone is familiar with variance reduction, the variance reduction rates for Saga, this is exactly how they look. So this is the noise term from before, and these things should look very similar to the Saga rates. And because of this, we are already better than federated averaging. So if you sample 1%, so typically we would expect to see like a multiplication of these two terms, but we actually don't. It's just like whichever of these two is smaller is what affects the rates in the strongly convex case.
So would it be possible to describe the scaffold method as a local Saga? Would it be fair?
Probably.
Or there's some other differences?
So
just like you have SGD, local SGD, and Saga, local Saga. Would that make sense?
I think so. So there's this algorithm which is called distributed SVRG, which is, so it's a combination of this distributed SVRG versus, and using Saga for sampling. Yeah, I think it's fair to refer to it as local Saga.
So there's some questions in the chat box.
In federated averaging, devices do not communicate. In this, devices need to communicate. No, so everyone is always communicating only to the server, and the server sends whatever is needed. So the way you get the C is, so the server communicates both the model parameters and also the new C. So the communication is happening only to the server and clients. The clients do not communicate between each other. Yes, exactly. David Frey makes a comment makes an observation that if we needed to compute the gradients of all the other clients, they need communication, but because they use C minus CI, they don't need to communicate amongst themselves. That's correct. Okay.
So there's again a question by Tin. Apologies, you have so many questions, but I think it's great we have that much interaction.
Yeah, that's
Then
fine.
go
I mean,
ahead.
it'll also help me
Indeed, it's
improve
very
my
interesting
slides.
talk. So sorry for asking many questions, but
Thank you.
so using C and CI, you don't need to use the bound of G you have before, right?
Exactly, that's true. That's a good observation. That this does not need assume any assumption on the similarity. G does not matter at all.
So just another comment, maybe to following up the comment from Peter. So there's another method which maybe not common in this community, but they call gradient tracking. So this
Yes.
is kind of like local version of that, or like they similar in the concept.
Yes, you're right. Gradient tracking uses a similar idea. There are some subtle differences, but yeah, broadly it's actually quite similar. Except that I don't think that gradient tracking tackles the sampling part. But yes.
No, there's some paper, but yeah, you're right. Yeah.
That's a good observation. Yeah, so there's just one final point I want to make before. So, okay, we saw some rates, but these are actually quite not so satisfactory because if we just use Saga, then the rates we get would be the same as this. There is no advantage to taking k greater than 1. Why? So we made sure by doing scaffold that we're not worse. So taking k greater than 1 does not hurt us, but it's unclear whether it helps us. And at least from the theory so far. And there's a lower bound from I'm not sure, 100% sure how to pronounce this. Sorry if I get it wrong. Aryavani and Shamir from 2015 have a nice lower bound which shows that in general, you cannot really show that local steps help. Like in general, taking one step is as good as you can do. But there's a way around this lower bound if you assume your Hessians are similar. So this is like the final point I want to make, which is if you assume your Hessians are similar, which is if you assume that the Hessians are delta close to each other, and that every function is delta weakly convex, you need this because you need this to say that when you average things, things don't blow up. If it's completely non-convex, when you average, bad things happen. So that's why you need that weakly convex. But mainly you need to, if you assume that your Hessians are close to each other with some delta factor, then you can prove some improvements. In particular, always this delta is smaller than the smoothness constant L, but typically it is actually much smaller than the smoothness constant L. And if you assume this, you can prove some improved rates. At least, so in scaffold, we show this for quadratics, but we have since been able to generalize this for arbitrary functions, which shows that the basic at a high level, what you can do is you can replace the smoothness constant L with this delta. So previously if in the non-convex case, it was L over R here. Now it's delta over R. So, which means that we've actually managed to actually prove a rate which is much faster than SGD. So I don't want to get, I don't have time. I think I'm already over my time. So I won't go into too much details about this. There's some nice repercussions to this result. It says that the number of local steps you should take is actually roughly proportional to this L over delta. Delta is always at least smaller than equal to L. So if delta in the worst case is equal to L, so then you should just take one local step. But if delta is much smaller, then taking more local steps actually helps. So in the rates, essentially intuitively, we replaced L with the delta. And so we actually have first rates which show some improvement due to local steps. yeah, maybe Peter can comment. So this is all that I wanted to say. There's some experiments, but maybe Peter
So
can
feel free to
comment on
go
this.
through the experiments. So we are recording this. People who need to go, they'll go anyway. We're not holding them here, so feel free.
I forgot to
Feel free.
press record. Is it all?
So we're recording this as well.
Ah, okay, perfect. Okay, that's great.
Do not worry.
Okay.
So
yeah,
take
thanks.
take some extra time to go through the experiments, and then we'll go
Perfect.
to the final questions.
Yes. So these are some just simple experiments. So these are just like on some scalar quadratics. This is actually the lower bound construction we had in the proof. So in dotted line is the SGD rate. Right? So SGD has some nice linear convergence, but if you take federated averaging, okay, if this G is small, so this G controlled the amount of heterogeneity amongst the clients. So if G is small, it's fine. But as G increases, you see that federated averaging gets worse and worse when compared to SGD. On the other hand, SCAFFOLD is completely unaffected by this G. Like these three plots look identical. So it's completely unaffected by this heterogeneity. And also for SCAFFOLD, larger the number of local steps, you do see an improvement. K equals 2 is better than K equals 1. It is in fact 2 times faster, but K equals 10 is only 4 times faster. So this is actually related to our delta definition. So there is a limit to how much you can expect, how much improvement you can see. And this limit is controlled by this delta thing, which we briefly discussed. So this was just some toy example where we could control both G and delta. Now some more real world examples. So this, if we take this extended MNIST, balanced extended MNIST dataset, it's a multi-class logistic regression problem. It has about 47 classes. So we just partition it into n clients. N is, I think in the results I'm about to show you, n is 100. The way it's partitioned is we first sort them by labels. And then depending on how, if you want to control the similarity, what we do is with a small probability, we'll take a sorted thing and put it at a random place. So if similarity equals 0, this means it's completely sorted. If similarity equals 100, it's completely shuffled. So it's IID data sets. And similarity 10 is somewhere in between. Similarity of 10% means it's sort of 10% shuffled. Okay, so with similarity equals 0, I think this is like 5 local steps or maybe 10 local steps. Sorry, I don't exactly remember. And we sampled 20 clients out of, okay, this was 400 clients. And we see that, so this is like the training loss, the train accuracy, and the test accuracy. So in all of these, SCAFFOLD in yellow is much better than both SGD and federated averaging. And in all of these, federated averaging is actually worse than SGD. So all the extra gradients, all the extra work we're putting in by taking local updates is wasted. You might as well just do SGD. So, and this is true for the loss, this is true for the train accuracy, and it's true for the test accuracy. So this shows like what happens if you change the similarity. So with similarity equals 0, SCAFFOLD is way better than anything else. SGD is over here, SCAFFOLD is over here. Both SCAFFOLD and SGD, as you change the similarity, they remain unaffected. It doesn't matter so much to these algorithms, but it has a big impact on federated averaging. For completely IID data, federated averaging and SCAFFOLD are identical and they're both much better than SGD. And if you have like in between, federated averaging is actually better than SGD, but SCAFFOLD is still slightly better. So depending where on the spectrum you lie, federated averaging might be a very good idea or a horrible idea, but SCAFFOLD is always it's a safe algorithm to use. And this just tries to
There's
see.
a question by Konstantin.
Yes. Does it converge to the same test accuracy as SGD eventually? So this is a convex experiment. Because it's convex, and everything converges to the same point. So it does, scaffold does converge to the same test accuracy. Federated averaging, it depends. You have to tune the step sizes carefully and so on. So I think we ran it for, so this shows just for 500 rounds. We ran it for 1,000 rounds. And SGD does eventually, so this is actually about, it doesn't really improve much better than this. So SGD eventually catches up with scaffold, but it takes much longer. But for the non-convex case, it's a pretty good question. There is a potential, it is possible that scaffold and SGD converge to different points and have different test accuracies.
So I have one generic comment here. So it is very obvious that scaffold is much better here than the other algorithms. And there's this alternative point of view, which you mentioned, that this work of Philip and mine, that variate averaging could be seen as simply solving a different problem. So I think this needs to be kept in mind for the audience, that somehow, yes, if we insist on this problem, which variate averaging is saying it's solving, then scaffold is much better. But it also makes sense to ask, what is actually variate averaging doing?
Yes. So this assumes that exactly. So this is all assuming that we want to solve. So this all assumes that we want to solve this global function, and there's some additional. If you want to do this personalization and so on, I think we are seeing a talk about this next week. So tune in again. Bye, Philip.
Thanks for the advert. Yeah, there's a question.
So there's a question from Arseni, which asks, in the motivation, you convinced us that SGD is better than FedAvg. What changed here? That's a great question. So if you look at the similarity equals 0, federated averaging is actually worse than SGD, and it is a bad algorithm. But if as your similarity increases, what is happening is that the G term doesn't matter so much anymore. And then if your G term is small, there is a chance that federated averaging can be better than SGD. So I think this was a point brought up once before. It's a question of how this heterogeneity across the clients versus heterogeneity within the client. Like, it depends on where on this balance your method lies between federated averaging and SGD. That's a great question, though. Yeah. So
there's one question by Edward. He wants to ask.
Yes.
Using his own voice.
Yeah. Hi, Praneeth. I want to ask about step sizes in experiments and in theories that you use. So, are there any differences between theoretical?
Pretty much any figure I showed you use step sizes which was tuned individually for each of the figures. It has nothing to do with the theory. We just tune the step sizes.
Okay, but do you use the same step size for SGD as for scaffold?
In these experiments, so okay, we did do a search over, or we definitely did a search over step sizes, but I don't remember if the best step size for both ended up being the same or not. I think, okay, so I think for similarity 10 and 100, it actually was the case that the best step size for SGD was the same as the best step size for scaffold. But for 0%, I think the step size for scaffold was actually slightly smaller.
Oh, okay. And then another question: could you show, please, the slide with complexity guarantees for scaffold?
For general functions or for?
Yeah, for this one,
yes.
yeah. And so am I right that in this, for example, for the strongly convex functions, you use the same step size as for SGD, or
no.
let's say if S is just n when we sample all clients, okay?
So for this rate, the step size actually needs to scale down with the number of local steps. So if you see this term carefully, there is no real advantage of taking local steps. That's because step size we chose actually needs to scale down with the local steps. So the step size which comes out of this theory, I don't think is very reflective of what goes on in practice. I think actually the step size which comes out of this theory is what is more reflective. Here, the step size depends on this delta factor.
Yeah, and how does it scales for general heterogeneous case? Not this one, but for the previous setting. Yeah, I mean,
it has to scale. So the step size is like a minimum of like 3 quantities, and one of the quantity has k in its denominator. As the number of local steps increases, your step size decreases.
So, and am I right that it is typically smaller than for SGD?
Yes.
Like for mini batch SGD.
Yes, it is. It is smaller.
And anyway, optimization term is the same as for mini batch SGD.
Yes, except that there's this variance reduction part.
Yeah, but when S is n, then we don't.
Yes, they're the same. They're the same.
Yeah.
If S equals n, the rate is the same as mini batch SGD.
Okay, somehow these local steps, they help to use smaller step sizes, even for heterogeneous case. Am I right?
So
in comparison with mini batch SGD.
So what is happening here is, so in the worst case, that's actually related to this part. So in the worst case, your local steps cannot help. So in the worst case, what you would need to do is, if you insist on taking k steps, you need to scale down your step size by k, such that k local steps of scaffold sort of look like just one step of SGD.
Yeah, and
so in the worst case, you need to scale down your step size such that your k local steps together just look like one step of SGD. But if things are usually not worst case, and so you can use slightly larger step sizes for scaffold.
Yeah. Okay. Thank you a lot.
Thanks for the questions.
I can see a question in the chat box by Taha Togani.
Is it a must for, yes, the question reads, is it a must for all clients to have a copy of the model in the server? So I think what you mean is, do the client have to, so if I understood the question correctly, in each round of scaffold, we need so the client I needs the CI, which is computed in the previous round. And so this needs some additional memory and has to be stored somewhere. This is actually a great observation. And so the way we implement this is we store the CI on the clients themselves. So each client stores the CI from the last, say client 1 participated in the first round, and then it again was called in the 10th round. So in the 10th round, it uses the CI which it computed in the first round. So this clients need some state to so the clients need some persistence of state, and this is exactly why I said that this one scale, if you have millions of devices right at the beginning, and this is like the main limitation of Scaffold, right? If you have like a million clients, say, imagine you want to run this over all Android phones, it's quite unlikely you can run Scaffold in this setting because each phone will probably be seen. Taha comments, suppose Google wants to train BERT with all the Android phones. Yes, you cannot. It is quite hard. Maybe Google can do it because they have super large resources, but it will become very memory intensive to run Scaffold in this setting. This is more for when you, this is perfect when you have like say 1,000 devices or 10,000 devices or something like this. So the main takeaways is that FedAvg has a degradation due to client drift. This is not just theoretical, you can actually see this in practice and is corroborated by loads of other experimental papers. But if you have to use federated averaging, you should use a separate server step size and a client step size. And then why should you use Scaffold? At least in the setting where I talked about, it is a completely parameter-free method in the sense that, okay, it does not use new parameters. Like whatever it was there for SGD, it's the same parameters. There's no new parameters introduced. And it probably converges faster for faster than SGD and federated averaging. And it is resilient to this heterogeneity. And this main limitation is what Taha pointed out, which is that you need to maintain this client state. But we have a new paper which tackles that setting. Keep a lookout on arXiv over the next couple of days for this. So if you do want to train BERT over all Android phones, this new method MIME is what you should use. It talks about how to use momentum, Adam, and so on, and some nice theory. And there's some other questions. So here I mentioned two, which is related to this Byzantine robustness, which we saw a talk on last week. This paper may be interesting to some of the people here, because there were questions about how do you do Byzantine robust learning when you have non-IID data. So keep a lookout on arXiv for this. And there's some papers about one more thing about how to combine privacy. Other super cool directions are what Peter mentioned, and how do you combine this with personalization, which I think we'll see a talk on next week. But there's like plenty more directions, I think, in this.
Thanks, Praneeth. This was fantastic. You've got probably 150 questions.